Pushdown automata. What we've done so far in automata theory is we've looked at modelling the real world scenarios, and that was grand when we had what we called our regular languages. We could represent those by regular expressions. They were all the nice things. Typically anything that is finite can be represented by a DFA or NFA. It can also recognise infinite things. But we found out that there were certain languages that DFAs and NFAs could not recognise. These non-regular languages, which now, because of the pumping lemma, which we were doing in the tutorial and we were doing last Thursday, we can identify which languages are non-regular. But they can't be represented by an NFA or DFA, and this is where pushdown automata comes in. So pushdown automata is going to be a machine, a model, that is going to be able to represent or depict the method that is needed to sort of recognize a non-regular languages. And some of these non-regular languages were quite useful. So even very simple things like 0 to the n, 1 to the n, so we've got n zeros followed by n ones. We can't determine we can't recognize that language with a finite automata in form of a DFA or NFA. And what we were beginning to see in the tutorial last week is where we cannot recognize something with DFA and NFA is if there's a relation between this power and the next power. So if we had 0 to the I, 1 to the j, we didn't care how many zeros we had and we didn't care how many j or 1s we had, then we could recognize it with an NFA or DFA. What fell down is we have to keep track of how many zeros we have and make sure that there's the exact same number of ones followed after. So I think we actually did this one last week either in tutorial or in class. We used pumping lemma to prove that this is a non-regular language, and therefore DFA and NFA can't recognize it. But these pushdown automatas will be able to recognize it. They'll look very similar to an NFA, but they'll have some slight, more complex transitions. The main thing that we want to have in this model that we didn't have in NFA or DFA is memory. So we couldn't keep track of the number of zeros, but what we're going to introduce is some form of memory that will allow us to keep track of how many we've got so far, and then essentially we're going to read back from that memory how many ones we'll have in the second half of our word. Now, have we done a stack in data structures and algorithms yet? Yes. Okay. So we know what a stack is. If we don't know, think stack of pancakes. Of course, we have two operations. We have push and we have pop. Push, you put something onto the stack, it goes onto the top of it. Pop, you take something off the top of the stack. So the first object in will be the last object out. Okay? Just remember those two operations of push and pop as we kind of go through. So in this instance, if we're going to push 2 onto the stack, it goes onto this empty stack. We generally represent it vertically, but if you want to represent it horizontally, that's absolutely fine. Doesn't matter which way you do it. If we want to push 0 onto the stack, then 0 comes on top of the 2. And now that is the most recent add-on into what our current memory holds. If we want to push a 1 onto it, again we just put a 1 onto the top. And if we want to pop a 1 off, we can do so because it's the most recent thing onto the stack. Okay? If you were to try to pop 0 at this stage, you can't do it because it's not the top element. So you can only ever pop something off the stack if it is the top element that you want. You can always push onto the stack. Essentially, this stack is infinite memory. There's no upper limit to how much you can store in the stack. You can just keep pushing things onto the stack. There is, of course, then a limit to how much you can take off the stack. So if you were trying to pop from the very bottom when it's an empty stack, it would just crash or fail. It's not recognized. If we were to pop 0 off then, we kind of, what we're doing this time is we're now reversing. And what we'll be doing, a lot of these pushdown automatas, we'll be storing information onto the stack that we want to store, and then we're going to take off and kind of reverse back what we have. So you continually push and pop onto the stack, assuming that you can pop in a legitimate fashion. And then you'll be left with some answer. What we're going to find is that a system, or this pushdown automata, will recognize a language if it ends up with an empty stack, okay, that has had something put on it and something taken off it. Or it could just be empty because it's essentially the null case, it's the empty case at the very start. So what you're going to find is if you ever have something left in your memory, essentially you've stored something there and it hasn't been removed afterwards, it probably won't be recognized by your pushdown automata. So here is an example of a pushdown automata. Now, if we look at it like this point of view, this looks very like an NFA. Okay, we've got epsilon transitions, we have accept states, we have some alphabets. The alphabet here is 0 and 1, and that allows us to transition between states. We've got an accept state, or two accept states, Q1 and Q4, but essentially it's just an NFA. What we have in addition to these parts are these new transitions, okay? So slightly more complex transitions, which now have 3 parts. And the 3 parts are very, very simple. We're going to try to do this in a practical way. The first part in transition is the exact same as in NFA or DFA. This is the input character. So if your input is, well, if epsilon the M string, or your input is a 0, if input is 1, then you're going to do something. The next character we have is something that we want to pop off the stack. Okay? So if you're going to have an epsilon, you're not going to pop anything off the stack. Again, it's an empty character. We then have an arrow, and the next thing after the arrow is what we're going to push to the stack. Okay? So say we had an input of 0, 1, 1. Okay, let's say we had 0, 1, 1. Now this is the language that recognizes any number of zeros followed by any number of ones, provided actually that they have the same number of zeros and ones. So we'll actually get something that recognizes. The first thing we do is start in Q1 as normal. We can transition using epsilon because it's the empty string, which gets us into Q2. With this stack function, what we say is you have a stack here which contains nothing at the moment. The first character is epsilon, so we're not going to pop anything off the stack. And that's a good thing because there's nothing on the stack to begin with. The next character we have is $. And we have to pop that onto the stack. Now $sign are special for the pushdown automatas that we'll be studying. Some people use different notation, some people use sed instead of $sign, but essentially this is just a starting character. So as much as epsilon is going to be your empty string, your $sign is essentially going to say that's the first thing I'm going to put on the stack. Okay? So the $sign is the very first thing you're going to put on the stack. We go into Q2 and we've got a 0. That means we stay in Q2 and we pop nothing off the stack because we've got epsilon, and we pop 0 onto the stack. So we put 0 onto the stack like that. We're still in Q2 and we get a 0 in, so we're here. We've then got epsilon, so that tells us to pop nothing from the stack, but we've got a 0, so we have to push 0 onto the stack. Okay. We're in Q2, and now we're looking at a 1. that says we have to transition down to Q3. The next symbol says we have to pop a 0 off the top of our stack. And what do we have to push onto our stack? Absolutely nothing, because it's an epsilon. Okay? So we've got a 1 in, so we'll transition to Q3. We're going to pop the 0 off the top of the stack, which we did. And then we're going to push onto the stack absolutely nothing. Okay, so it's a very formulaic process to go through. First thing is, what is our transition? Second thing is what we're going to take from the stack. And the last thing is what we're going to push onto the stack. We are now in Q3. Q3 says if we get a 1, we must stay in Q3. We must pop a 0 from the stack. And what do we push onto the stack? Absolutely nothing, because it's an epsilon. Okay? So our stack remains unchanged after we pop 0 off. We're in Q3 and we have nothing. So we're going to use our epsilon transition into Q4. So we move into Q4. What does it tell us to do? It says to pop a $sign off the stack. So that's what we do. We pop a $sign off the stack. What do we add into it or push onto the stack? Epsilon. So we push nothing onto the stack. And we finish in Q4, which is an accept state. Okay? So we started off by saying this machine apparently recognizes all those words which have an equal number of zeros followed by an equal number of ones. We should accept this word 0011. What we find is we do end up in accept state. And how we did it was every time we got a 0, we stored it on a stack. We kept it in memory. Then for every 0 we had, we essentially removed one. And that meant for every 0 we got, it got cancelled out by one of the ones, and we get left with an empty stack at the very end. Okay? And that's what we're looking for if we have a pushdown automata. Okay? So the 3 things, you just go through the process. Let's say, we'll take a different example. Because this is essentially an NFA at the heart of it. So it's not accounting for every eventuality. So say we get 0, 1, 1, okay? We start in Q1, and we'll use our epsilon transition, or empty transition, without reading from the string, and we'll move into Q2. We take nothing off the stack, we pop epsilon, or take nothing off the stack, and what we push onto the stack then is our $sign. We're in Q2. What should we do in Q2? We're now reading our first character. So what should we do?
There's 0 on the stack.
Put 0 onto the stack. Do we take anything off the stack? Nope. We just put 0 onto the stack. Good. And we stay in Q2. We get a 1. What should we do?
Pop 0 on the stack.
Pop 0 from the stack? Yep. What do we put onto the stack? Nothing. And where do we move to? Q3. So now we're looking at this one here, and we're in Q3. So we get a 1 in Q3. What should we do?
Stay Q3.
Okay. Can we pop a 0 from this stack? No. So essentially this crashes. So this doesn't have kind of are accepted, and this word here can't be accepted by this machine, and nor should it be, because that's not the language of this pushdown automata. For this to be accepted, we need an equal number of zeros and an equal number of ones. So if you find yourself that your machine essentially crashes because this path that you've gone on tries to pop something off the stack that doesn't exist, that means the word won't be recognized. Okay? But this is the approach that we're going to take. Yeah?
See, does this, the way that you have 0 everyone in, does that mean it's all zeros at the start of n ones? But what if it was like 0, 1, 1, 0?
Then, so 0, 1, 1, 0.
Yeah.
Yep, as an input string.
Yeah.
So let's do this one. So now we've got a 0 would push the 0 onto the stack here. This 1, again, we're still going to be in Q3. We'll end up the same point. So sorry, we've got a 0 in, we push it on. We get a 1, that means we take it off, because this is the transition from Q2 to Q3. We get another 1. We try to take off a 0, but it's not there, so it crashes again, and again this word fails. This language has to be all zeros concatenated with all ones. So if you were to write a language like that, it could come from multiple languages. But this particular one is zeros concatenated with ones. Anything else then before we move on? Okay. Now I apologise to anyone who's printed off the notes, because we're about to rattle through about 8 slides that we just did there in like 1. So we've just essentially explained everything that is actually written down in the notes here. So we'll go through to see how far we need to progress on. But do remember, our special symbol, $, is just saying we've started, and then at the very end we finish. So when you're actually constructing these pushdown automatas, one of the first things that you should really do is you have a start state. And notice that our start state is an accept state. Why is it an accept state? Well, in these cases, because, for instance, in this language, n is greater than or equal to 0, so potentially we could have no zeros followed by no ones. But equally, our stack is empty. And for us to recognize a word, we should end up with an empty stack at the very, very end. And at the minute, we're starting with an empty stack like that. Okay? So we'll accept. If we then want to progress into our machine, the first time we do so, we move into our machine with epsilon. Okay? We then take nothing or pop nothing off the stack, and we put on our special symbol, our $. Okay? So when you're constructing the PDA, your very start state, you can almost draw instantly. You can then draw your first transition into the real machine, if you like, that will actually process this particular language. And you do so with your empty transition. You take nothing from the input string, you pop nothing onto your stack, and you push then on the symbol for our $. And equally, when you finish, you're going to have some end state, some accept state, or some finish state. And how you get there is going to have to be by epsilon. You're going to pop off $, and you're going to push on nothing. So essentially, you've started by taking nothing from the word. You have popped nothing off, but you've put on a $. When you're finishing, then you do everything in reverse. So again, you take nothing from the string, because this is after the word's finished. You're going to then pop off the $, that you originally put on the start, and you're going to push nothing on. You're going to leave the stack completely empty for the end. What's this? Yeah. Okay. We haven't mentioned that this is slide 16, sorry, for anyone who's got the hard copy of the notes there. We did mention that this is based on a non-finite automata, or sorry, non-deterministic finite automata, an NFA. And there is non-determinism within this machine, okay? So we already found it once in the sense that when we got a when we try to pop a 0 from the stack here, on our example 0, 1, 1, we had nothing to pop, so it wasn't kind of deterministic. We didn't have all cases covered. But we've also got the option here to go through multiple different paths, okay? So for instance, if I take a string 0, 0, 0 followed by 1, 1, 1, the first thing you can do is just start in Q1, okay? And pretend as if you're going to read a 0 from that point. Or well, let's take what we've done so far. So if we take the epsilon and then we move into Q2, we can push our $sign on. The other alternative is that we actually read a 0 at the very, very start. So we're in Q1 and we try to read the 0. So at the very start of the machine, we could have taken from the word, or we can jump using epsilon. If we try to read from the words, so we're in Q1 and we try to see what to do with the 0, it's undefined. Okay? So what will happen? It'll crash. And then this thread essentially just dies as normal. And we've got another path, S2, which will carry on and process on the word. So as much as in our NFAs, we had the option to go down one path or another path, we will have the same thing here. So in this case, when we started at the beginning, we could have actually looked for a 0, because that was the first character. If we tried to look for a 0, it's undefined, that thread will crash or die. And then we have another option. Option 2 is that we use our epsilon transition and move into Q2, and then we can see how that word progresses as we go through. And that side is, of course, well defined. This word should be accepted in the end. This has an equal number of zeros and an equal number of ones. Again, just to move through towards our main point of this, because we've already covered a lot of it. The main thing is we have 3 zeros. What our machine has done is push 3 zeros into memory, and what it will then try to do is take away 3 zeros back. So for everything you pushed on, it wants an equal number in return for the number of ones, so then it's going to remove them with our pop. And again, this is just going to try to reverse everything that we did the old way. Now, again, at this stage, we've also got non-determinism. So if I get a 1 in here, I move into Q3, and then I've got the option of taking a 1 and popping off a 0, and then pushing something on the stack. In this case, pushing nothing onto the stack. So I'm in Q3, and I get a 1. I can just follow this transition to pop a 0 off and push nothing onto the stack. The other option that you have when you're in Q3 is that you can not take from the input and you can use epsilon to jump into Q4. That's a valid thing to do. So once you get a new path that the PDA can go on, you create a new stack that it could possibly take. Okay? So for each path that you have through this machine, you will have a different stack. And essentially it's the same thing as before. So you have multiple paths through your machine. So you have some start state. We may venture off into one direction or another direction. Some of them may crash. Provided that there is a path that will accept, then the word is recognized, just like an NFA. And for each path that you have, you need to create a stack. Okay? So essentially, you're trying option 1, and you're taking a piece of memory, and you're going to build up the stack for that particular option. Who knows what will happen with that? It might crash, it might accept. If you've got another path, then essentially you're going to have to start from scratch. Create a new piece of memory for that path and build up the stack there. So the bottom line here, and the main reason behind this is when you're going to be doing examples on PDAs, you may have to create multiple stacks, okay? And that's fine. You just have to remember which stack belongs to which path, and you pop something onto the stack that's related to the path that you're currently on. So for instance, stack 3 here, stack 3 came from getting an epsilon jump into Q2, getting 3 zeros and popping 3 zeros onto the stack, and getting a 1 and popping a 0 off the stack. So that's why we're left with 2 zeros. Then we've used an epsilon to jump to Q4. Epsilon says to pop a $sign off the stack. We can't pop $sign off the stack because it's not the top element. So this one will crash. And then stack 3 actually becomes null and void. We don't care about stack 3 anymore. And we can create stack 4 and we can create stack 5, because if we're in Q3, instead of going through this one transition, for getting a 1, popping a 0 and then putting nothing onto the stack, we could always just jump with epsilon. But we're going to fall into the same problem time and time again. It will crash. So this is another example. So we've gone through the loop once. We have popped off another 0. But then instead of going through this loop transition again, we decided to jump through. And this is our stack 4 now. We got to stack 4 by going epsilon into Q2. We put our $sign on. We then stacked 3 zeros onto, we pushed 3 zeros onto our stack. We popped off 2 of them. And then instead of iterating on this loop one time, we've just used our epsilon jump. Got to here. We've tried to pop a $sign and again it crashes. Same thing will happen if we loop through this one more time. We're in our last one. And potentially we could have jumped to epsilon a little bit too quickly. Can we pop a $sign off? Yeah, in this case we can, because we're at the end of the word. And we will accept. We end up with an empty stack at the very end, and we finish in Q4. So do we accept or reject this word? We will accept it. Okay? Same as NFAs. If there exists a path that gets us to an accept state, then we accept a word. Not every single path will get us to an accept state, but as long as there's one of them, then we're fine. So we can use this stack for storing an unlimited number of zeros, okay? So it's not like real memory in the world where it has a fixed size. It's a theoretical piece of memory, and we can continually stack objects onto it. So we won't be able to run through every single iteration of n zeros followed by n ones. That's not possible to do so. But this machine theoretically could. We could potentially stack infinitely many zeros on, provided that at some stage we come and remove every single zero, or with our ones. So, how would we formally define our pushdown automata? Okay. Looks very, very similar to an NFA or DFA. What's the difference between NFA and DFA and this pushdown automata?
It has a stack alphabet.
It does, and the transitions are different. Okay? So the states are exactly the same. The input alphabet is exactly the same. The start states are exactly the same and denoted in the same way. And our accept states are the exact same. The difference is now we have things that could be stacked into memory, or could be pushed into memory. And we could have things, our transitions are different because we now have 3 components to our transitions, okay? Now, our states, very obvious, Q1 to Q4. Our input alphabet is our first character in each case, okay? We don't put epsilon into our input alphabet because it's within every single possible input alphabet, okay? Our stack alphabet. Does anyone have any suggestions of what our stack alphabet might be? You're saying 0, 1. 0 and $, good. So just because we have something as an input, that doesn't necessarily mean it'll be saved to memory. So our stack alphabet is everything that can be saved, which is $, and a 0, okay? So it's the very middle component of our transition triple. So it's all our, everything that you can push onto the stack. Sorry, it's the second thing. Well, actually, it's the middle and the last thing. So everything that you can pop onto the stack, pop off the stack, should have been able to push onto the stack at some stage. Okay. So our second and third components both come from the stack alphabet. And again, epsilons nominally within the stack alphabet, we don't denote it because it is a special character in its own right. Our transitions, they are a little different. Okay? Let's look at our three things that we need in transition. We start in, this is for, yeah. So what we're used to seeing is if we have a state, we need to know which state we're in, what our input character is, and generally what state we're going to. With this one, it's slightly different. We need to know what state we're in. We need to know what to do with the particular input character. We also need to know what to do with something on the stack. So what are we going to pop off the stack? And then we're also going to need to work out what we push onto the stack and essentially where we go to after that. Okay. So our first 2 components would be our state, what our input character is, and then this B is kind of the top of the stack currently, and then at the output of it, C is the end of what the stack is after we've done our transition. So essentially B is what we're going to pop off the stack, and C is what we're going to push onto the stack. And then of course with any transition we do have to transition to a state. It may stay in the same state, but we have to transition to a state, and that's where Q2 comes in. So formally then, we'll just get through to the, because we have actually talked about all this that we're going through. We'll get through to the formal definition in terms of sets. So if we take each of these components, our states come from Q, which is a set of all states. A is, of course, our input alphabet, which could also be epsilon. So we have sigma union epsilon, which we can write as sigma epsilon. We have our transition alphabet, anything that can be used to pop or push onto the stack. And again, we can pop or push epsilon onto the stack. Q2 then of course is a state, it's what state we end up in. And the last one is of course another part of the transition alphabet. It's something that is pushed onto the stack. And of course we can also push onto the stack epsilon. Now I know I rattled through that quite quickly. Believe it or not, we have actually spoke about what's in the notes. What you have in your notes is kind of your formal thing that you can always go back and read. So don't panic that we went through a lot of slides very quickly. But does anyone have any questions? Because we did kind of push through that. Any suggestions or any questions? what you're going to find is we typically will not do a transition diagram in the same sense as we did for an NFA or DFA. The reason why we don't have a transition diagram in this case, for an NFA or DFA it was fine, we had two parts to it, so we can draw it in a table with horizontal and vertical columns. In this case we've got three parts, okay? So we'd have to do horizontal, vertical, and also then depth, okay? And we can't draw 3D matrices very nicely on paper, okay? So that's why we typically will not write the transitions out on formal paper. So when you're asked to do a PDA, you'll typically be asked to illustrate the PDA using a finite state machine such as this, okay? So formally it does have a definition. It's defined in 6 parts. It's the same 5 parts as our NFAs and DFAs, but now we have our transition or our stack alphabet. That's our 6th part. But we typically won't write it down formally the way we would the likes of an NFA or a DFA. Now, what I want to do, just to finish today, because this is actually maybe a lot easier than maybe it sometimes can seem. So I just want to go straight into an example. This is from tomorrow's tutorial, okay? And it's one of the practical examples that we found couldn't be done with an NFA or DFA. So one of the examples that we found out before was that you cannot write or construct an NFA or DFA to work out if a piece of code has a balanced number of braces. Okay, so if it has an open bracket, it also has to have a closed bracket. So essentially what your compiler does as standard. Okay, but yet our NFA and DFA could not do that because it couldn't keep track of the number of brackets that you had built up, and it couldn't also remember how many to take away in the case of closed brackets. So it's very similar to our zeros and ones. We can store on our zeros and then we can take off our zeros when we get ones, okay? So our zeros could be every time we have an open bracket, we could put it onto the stack. If we then get a closed bracket, we then remove it. Essentially it is matched against one of them, okay? So what I'd like you to do is to construct a PDA that will recognize balanced brackets, okay? So essentially, we'll use square brackets for argument's sake, because it's like easier to draw. So for every open bracket, you must have a closed bracket. Now you could have open bracket, closed bracket, open bracket, closed. That's, we've got 2, 1, 3, 4. That should work. You have 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So they may not come in order, like the zeros and ones, but for every open bracket you have, you need a closed bracket. Okay? So remember what we said at the start. If you want to design a PDA, the first thing to do is to create your start state, your empty state as such, which will accept a null input. So essentially, if you have no brackets, then they're balanced by default. Okay? You then need to transition into this machine using our empty string epsilon. We're going to pop nothing off the stack and we're going to push on our $sign. That's our very starting thing. Our very end thing to do is, again, transition with epsilon out of the machine. We're going to pop off our $sign and we're going to push nothing onto the stack. Okay? So how will we think what goes in the middle? You're going to have to read in if it's an open bracket or closed bracket. If it's an open bracket, you want to remember that you've got an open bracket. And if you've got a closed bracket, you want to make sure that there was an open bracket to match. Okay? So have a think and have a go at that. Remember, you've got your stack. What are you going to push onto the stack? just like in normal NFA or DFA, just think for each input you have, what are you going to do? So take a couple of minutes and have a go at that, and then we'll regroup. Yeah. Okay, folks. So a lot of people seem to, we'll just come back together again. So a lot of people seem to have got this certainly intuition there with that one. It is very similar to this example in that we have to have a balanced number or an equal number of one thing compared to another thing. So we use the stack to store on information about the first thing, and then we remove it again for the second thing. Okay? We got the right idea. Some people will come back to this tutorial tomorrow, and we'll give the solution in the tutorial tomorrow. It also will be in the tutorial solutions anyway. But for anyone, a couple of people have got it with 4 states. If you think you've got it with 4 states, you can do it with 3. Okay? So look for loops and sort of repetition. So if you got it with 4 states, well done. See if you can get it with 3 states.